So we have Martin Pihl Andersen from DTA. So Martin is a researcher. He is doing PhD on high temperature heat pumps for industrial applications at the Technical University of Denmark. His current research focus is on experimental and numerical studies, especially on steam generating heat pumps. And he is also doing studies to implement the heat pumps in industrial applications to improve the performance and the robustness. He has previously worked also for large-scale heat pumps for district heating at Siemens, and he has a master's degree in mechanical engineering. So Martin, start your presentation. We are looking forward to it.
Thank you, Cordin. Thank you for the nice presentation. I will try to keep your attention and see if I can give you something of interest. At least I find it interesting, and hopefully you will do as well. So this has a bit of a different scope than many of the other presentations, as this is both testing and then afterwards modeling of an already existing heat pump that has been there for quite some time. So the one that I'm talking about is a steam generating heat pump by the company Kobelco, a Japanese company that has commercialized this product actually in 2011, most only in Japan, however. But that also means that they are already commercialized, and they are in a different path, let's say, they have already developed the product, and now they're looking forward to improving it to some extent. Right? Just to show you here how the product is created. It's a modular product based on a heat pump unit here to the right. Then there's a steam generating unit here as a flash tank that takes the water and creates it into steam. And then there's a steam compressor unit on top, as many of the other presenters has also presented earlier today. And these three units are then combined to create steam at upwards up to 175 degrees Celsius. So 8 bar gauge pressure, 8 bar absolute pressure. More or less, and then from heat sources 35 to 70 degrees Celsius is where it typically operates at. Steam heat capacity of up close to 1 ton per hour, and just to give you an idea of the COP, this is for the system COP, including also its auxiliary power. We get a COP of 2.5 for 165 degrees steam with a source of 70 degrees. As mentioned, commercialized in 2011, and that means that you have probably also seen that the refrigerant that is used here is the R245 FA and R134A, and that is something they want to change, and also want to look at both improving performance, right? So it's an existing system already working, operating for many hours in both in beer manufacturing and so on in Japan, but we want to future-proof it, and we want to increase performance as always, but we also want to look at lowering the cost of the system, for example, by removing one of these modular modules that it's consisting of. So the technology perspective is, well, we're looking into changing the refrigerant as it is now, as a drop-in replacement, business as usual, changing the R245 FA to either a HFO or hopefully more of a butane, and keeping the same operating range, making it future-proof that way, hopefully increasing performance at the same time. Or alternatively is that we switch to a refrigerant with a higher saturation, higher critical temperature, such as this HFO R1336 MZZ, or to pentane. As mentioned, they looking mostly into changing to the hydrocarbons, but HFOs are also still on the drawing board. And well, choosing to go for these either pentane or R1336 MZZ, we could potentially remove the expensive steam compressor unit to just have 2 units instead, and cutting the cost quite dramatically, the investment cost. And then the work that I will present here today is the different experiments that we have done, and then the following modeling to kind of show where what did we end up of conclusions and which directions to go. So the system that we try to do some studies on is kind of showed here, where we have the heat pump unit operating from 70 to 65. We are varying them. These are just indication of where we are roughly at design conditions. Then we have a pressurized water loop that is circulated to the condenser of the heat pump. And then this pressurized water is then increased some temperature before being throttled into the flash tank. This flash tank is kept at a level with some feed water, which is more or less the inlet of the condenser, you could say, to the heat pump. And then we take the steam and from the flash tank and put it into the steam compressor. This steam compressor is a screw compressor, which is injected with water to both prevent the superheat of it, but also to keep the clearance between the rotors and the casing to have the highest volumetric efficiency and isentropic efficiency possible. And then we have a drain separator after the steam compressor to ensure that we are actually supplying saturated steam and not just a lot of water together with the steam, right? But that also means that we have some drainage here that we feed back into the system. Just then, this is what we're testing, and then what we will model afterwards is a bit more details on the heat pump side, where, well, we will start modeling based on our experimental data. We will model the efficiencies of the compressors. We will model the heat transfer correlations of the heat exchangers to get a better idea of the performance there. And we will do this by, we will evaluate them in terms of COP and also economic evaluation afterwards in terms of both CapEx and lifetime operational cost. We change the source temperature from 35 to 70 degrees, varying it on through the range. We tested steam temperatures from 135 to 175 degrees. Flash tank temperature was a bit more modest in interval from 105 to 114 to be able to operate safely with the design of the flash tank as it is now. And then capacities from 280 to 535 kilowatts in heating capacity. And we changed the refrigerant 3 times. So both the standard mixture, and then we tried with pure R245 FA with 1224 YDZ, and then also R1336 MZZE. We wanted to try with butane as well to get even more data, but we sadly could not get a hold of the oil in Japan to do the testing when I was there. Anyways, but that is future work. So after running all of these tests, we made a model, as mentioned, and then we validated that model to see, okay, which kind of efficiencies do we get from the different components. Mechanical efficiency was relatively stable, independent of pressure ratio and many other factors. So quite, constant. I have removed the y-axis. Sorry for that. That's had to be kept a secret. But anyway, maybe ask me an indirect question. So close to constant and varying not that much, while the let's say the isentropic efficiencies and the volumetric efficiencies of the system vary quite differently from the pressure ratios when we varied the different conditions. So we had a declining thermal efficiency of the compressor with increasing pressure ratios, and then the volumetric efficiency is slightly decreased also. This is for the working fluid, so for the heat pump compressor, and you could see these clear trends. And similar for the steam compressor at the top cycle, we also had some trends where we put these into the model afterwards. So isentropic efficiency following kind of this polynomial depending on the pressure ratio, and then also the volumetric efficiency following some kind of trend. They were not as clear here because there were more other let's say factors that we could parameters that we could change to, for example, the injection rate and so on. And that's what we at least that this variation between the data is due to the injection rates being different depending on the operating point. But nonetheless, what we wanted was to model kind of the total efficiency of the system, and if we compare the efficiency of we achieve by the model and what we get experimentally, we are at least within 5%. One point is within 7%, and we are relatively happy with being able to predict the COP of that operating point. So then we had a model that we were relatively happy about, and then the idea is that we want to look at, from the modeling perspective, what is the optimal, let's say, for first of all, the optimal flash tank temperature of this, and that we did. So we try to vary the temperature here, keeping everything else constant, and seeing what happened to the performance of the heat pump. And what we kind of found out, which for some people might be straightforward for some, but what might be surprising to others is that depending on which steam temperature that we want to supply, the steam temperatures are then added here on the lines. We see 130 degrees, 140, 50, up to 170 degrees. And then with the flash tank temperature on the x-axis, we see that we have different optimum for COPs depending on our steam, the steam temperature that we want. That means that in principle, we should be able to vary the steam pressure, the pressure in the flash tank depending on what our optimal of the steam pressure that we want to supply. And the variation is flat to some extent, but still it has quite some influence on the COP. You will see from some of the further results that this influence is actually quite substantial compared to other effects. But yeah, we see these optimums, and these optimal points are at higher temperatures, the higher the steam temperature that we want to supply as well, which maybe not be surprising. But this is highly dependent on the efficiency of the steam. The actual, well, the shape is not depending on the efficiencies of the compressor, but the actual optimal temperature is very dependent on the heat pump compressor and the steam compressor. Yes. So the second one we wanted to look at was the we both wanted to look at both a high temperature steam supply, well, maybe not high, a low temperature steam supply with a low source temperature, and also then a higher source temperature and a higher steam temperature supply temperature. And we wanted to look at that for different refrigerants and see which kind of combinations gave the highest optimal, the highest COP, and also the economically best solution. And well, what we found to begin with is, well, a very blue plot in this case, as you can see, and that is to illustrate that the COP was very, very close to the same for the different heat pumps, independent on which kind of refrigerant we used. We modeled it both with the steam compressor and without the steam compressor, with some of the higher the fluids with a higher critical temperature. And well, yeah, as mentioned, not big differences, but we have a slight edge to some of the hydrocarbons like butane and here isopentane without the compressor, and which we were happy to see that the natural refrigerants won on this one to some extent for future developments. This was for a case for 65 degrees and 150 degrees steam. We also then calculated what is the capital investment of these configurations of heat pump, and we found kind of some of not really the same trends. We saw that the current system with 245 FA was actually some of the cheapest ones that we could find. This is specific cost in terms of euros per kilowatt of capex, and then depending on which kind of fluid we used, well, pentane was the most expensive one, while if we removed the steam compressor, we could see also here that we would have a lower investment cost, which kind of makes sense, right? But now we've tried to quantify it at least. And now that we have quantified both the operating cost in terms of COP and then also the capital cost, we could yes, first of all just look at it for a different temperature. So this is for 150 degrees steam. 120 it looks a bit different, but the trend is still the same. So we have that it's cheaper without the compressor, the steam compressor, and then it's a bit more expensive if we have to do it with the steam compressor. And butane is relatively cheap, but the cheapest is still the current system. And if we then take some of these the systems and combine the operating cost and capex, we see some trend where here I have plotted the levelized cost of heat, so a combination, a lifetime cost, you could say. So euros per megawatt hours delivered in terms of the entire lifetime of the system. And what we see is that many of the systems are again quite similar, independent on which kind of fluid we choose, and the most that our compressors and so on are really the dominating part in terms of the cost of the system, while the operating cost, which is the blue lines here, are the most dominating and not surprising, right? That the fuel for the heat pump itself and then for the steam compressor. And we can see then for the cycles without the steam compressor out here to the right, we have sure that the bottoming heat pump uses more power, but it's not really, it still uses less even than having both the steam compressor and the heat pumps. So what in the end is that this little power is used for the circulation pump in the steam flash tank, but the total levelized cost of heat becomes lower without the steam generator, for this case at least, because the steam compressor was a bit inefficient compared to the cycle. So there's also some developments here. But some of the conclusions that we were able to take from this is that the hydrocarbons seem to be capable of being competitive in terms of both performance, but also in the lifetime economics. We did make a successful drop-in tests of all of the refrigerants. We didn't have to change the operating system. We didn't have to change any valves or any kind when changing refrigerant, which shows a kind of robust system to be able to operate with different working fluids. And then in the end, one of the main takeaways was also that the compressor efficiency is kind of the key. So all of these optimal points that I pointed out really depends on any future development of the steam compressors and also the refrigerant compressor. So for that, I will say thank you for letting me speak a bit, and hopefully you find it a bit interesting. This work was done mostly in part with the SuPrHeat project, a Danish European EUDP funded project, and then also in collaboration with CRIEPI, the Japanese Technological Institute as well. Thank you so much.
Thank you very much, Martin. This was a great presentation with this very famous Kobelco steam generating heat